caching exploits what is called as the temporal and spatial redundancy, wherein if the CPU is addressing a certain address, then it is very likely that the same address would be accessed again in the future, right? So that's called the temporal aspect. And then there is a spatial aspect where if an address X is accessed, then it is very likely that the following addresses X plus N are likely to be accessed. So there are benefits in caching this data. Caching is nothing but keeping the data very closer to the processor, because accessing the main memory and getting the data is very costly, because the DRAM tend to be much lower. So instead, what the CPU does is this temporal and the spatial addresses, it keeps it very closer to the CPU in very fast memories, right? So that's caching. And cache coherency is nothing but, I want you to focus on the right hand top. So in a multiprocessor system, right? So it is possible that each of the processor has its own caches, shown as C1, C2, C3. And it is possible that multiple copies of the same address exist in these, in these processor caches. So one of the important issue here is, assume, for example, there is an address X which is there inside C1 as well as in C2. Say if the processor writes into address X, so when the processor P2 reads that address X, it has no way to know that that address X actually has been modified by P1 when it wrote into that address X, right? So this creates a problem, because the data corresponding to those addresses are not coherent in the cache C1 and C2. So this is at a very high level cache coherency issue, right? So it is important to kind of remove the copies of those addresses if it is present in the other caches when you try to attempt to write into these shared memory addresses. So that's how you resolve those problems. So to take care of it, there is what is called as a snooping mechanism, which is shown in pink color, right? So this mechanism allows you to store the information on the state of the cache lines, right, inside the caches. So once you store these state information, it becomes very easy to resolve the conflict and provide the actual data which is requested by the processor appropriately. So that is the job that is done by what is called as a home agent, right, which typically resides inside the host. And it does all these functions using what is called as a directory structure that it maintains about the shared state of the caches and the cache lines basically inside the caches. So that's a snoop mechanism. And one of the popular cache coherency protocol that is implemented is called as a MESI protocol, MESI. It's pronounced as MESI. And apparently CXL also uses this MESI cache coherency protocol, right? So there you have 4 states for the cache lines, right? Typically a cache line is of 64 bytes. So for every cache line at cache line granularity, some state information is maintained as, say, invalid. When you say the cache line is invalid, that means it is not cached in any of the caches in the CPU. And when you say the cache line is in a shared state, that means it is cached in more than one processor, and the memory is up to date. When you say memory, it is let's say the main memory in this case. So main memory is up to date, and it could be present, the cache line could be present in more than one processor in the shared state. In the exclusive state, one processor, which we can call them as the owner, has the data, and the data is clean, which means it is in alignment with the data that is present in the memory. So that is, but it is not shared by the other processors. That means it is in the exclusive state. And then we have the modified state where one processor owner has the data, but it is dirty. For example, a processor could acquire a cache line in an exclusive state, and then it can keep modifying that cache line as many times it wants, because once you acquire it in an exclusive state, it goes to that processor, and then once you modify, that copy is actually present only, because it is present in only in one cache, it is okay to do it, and then finally it will do a write back, right, after it is done with whatever it wants to do with the cache line. So this is messy coherency protocol in short. We will now focus on the much awaited Compute Express link. So Compute Express link is a open standard off-chip interconnect, right, which is built on PCIe Gen 5. As we saw, it addresses the coherency, cache coherency aspects, and it also supports memory semantics to access the data and the memory, and it is also low latency. We'll see why it has a low latency subsequently, but for now it supports low latency and high bandwidth processor interconnects for accelerators, memory, and smart IO devices, maybe a network interface card, or as I told you, computational storage devices, etc. Right? And Spec 1.1 was released almost a year ago. Right? So 1.1 is publicly available, and Spec 2.0 is in progress. CXL protocol. So CXL protocol mainly at the say the transaction level talks about CXL.io, CXL.memory, and CXL.cache. Three protocols make up. These three protocols make up what is called as the CXL protocol, and it is built on top of what is called as a flex bus core, which is nothing but a PCIe 5. And on top of that, you could have the CXL or the PCIe protocol running. Right? So that's Compute Express link for you. Now diving a little deeper. So we saw about various transaction, various layers of the PCIe. So the CXL transaction layer, if you zoom a little bit, the CXL.io, as we saw in the earlier slide, CXL.io transaction layer pretty much looks like the PCIe transaction layer. And for the most part, the spec refers only to the actual PCIe specification. But there are some enhancements that are done to the transaction layer. Right? And for CXL.Cache and CXL.Mem, so they share the common transaction layer, and it is new. And that is what is dealt with in detail in the CXL specification. And then there is a CXL link layer. Similarly, CXL link layer is for CXL.io, and it is built on the actual PCIe, whereas for the CXL.Cache and CXL.Mem, so there is a new specification which is addressed in the CXL specification. CXL.Cache and CXL.Mem again share the common link layer. And then below that, there is what is called as a CXL R/MUX, right? So, if you can recall, PCIe is a packet-based protocol. Right? So, PCIe packets typically can be 128 bytes, B-Y-T-E-S, bytes, and it can go all the way up to 4 kilobytes, right? So that's how the PCIe works. So that's one reason, as I told you, if I have to access a cache line which is 64 bytes, and if I go on PCIe and access a cache line, so you will actually be very inefficient when you do it, because you need a larger packet for PCIe. Whereas in the case of CXL, they have defined what is called as a FLIT, F-L-I-T, FLIT, which is 512 bits, right? The 512 bits make a FLIT. So you could actually, the FLIT boundary is defined as 512 bits. So at the CXL ARB level, right, arbiter and the MUX level, So you could actually mux the CXL.Cache and the CXL.Mem flits at the 512-bit boundary rather than at let's assume 128 byte for a PCIe packet, right? So if there is a huge PCIe packet moving and then there is another transaction behind that, you need to actually wait for the entire packet to move so that you could send the next packet. Whereas with this flit mechanism, it becomes easier to break that transaction at the flit boundary and then send the subsequent transactions. So that way, CXL achieves low latency. So these flits are fixed of fixed bit length of 512 bits plus 2 bytes are also there for sending the CRC information. So that is what happens at the org level, right? It muxes the transactions coming from the CXL.Cache, CXL.Mem, and the CXL.io as well. And then, so they are sent over the file, which is again borrowed from the PCIe. So that is about the various CXL layers. And regarding the CXL protocols, we did see in the previous slide. So CXL.io protocol is basically nothing but it is the PCIe based non-coherent IO protocol, which is same as the existing PCIe protocol. And then we have CXL.memory. So CXL.memory is for memory access to support device attached memory, right? And CXL.Cache is for coherency that supports device caching of host memory. So if the device wants to cache the host memory, then that CXL device has to implement this protocol CXL.Cache. So CXL.io, memory, and cache are the three CXL protocols that are defined in the CXL. Then the CXL standard also defines different types of CXL devices. So one is called type 1, and then there is a type 2 CXL device and type 3 CXL device. Let's understand what each of this type means. Right? So for the type 1 CXL device, you have to implement the CXL.Cache and CXL.io. CXL.io is mandatory for all the CXL devices, right? Whether it is a type 1 or type 2 or type 3, CXL.io is mandatory. CXL.io is required for configuring the device and the device discovery and other mechanisms. Other non-cacheable access also go over CXL.io, so it is important to implement it. And for the type 1 device, CXL.Cache is to be implemented because these are kind of devices that cache the main memory addresses or the host addresses. So that such kind of devices will implement CXL.Cache. And then for type 2 device, so they are, you can imagine them to be like accelerators, right? Which will have its own memory. For example, GPU, which will have, which could have a high bandwidth memory connected to it, and it will be used by that GPU for doing its own operation. At the same time, it might also be caching some of the, the host addresses inside. So it could have a private memory. It can also cache some of the host addresses. So such devices should implement CXL.Cache, CXL.Mem, and CXL.io. So they are called as type 2 devices. So as part of this type 2 device, the spec defines two modes, what is called as a host bias and the device bias mode. Right? So type 2 CXL device also allows the host memory, the host CPU to access the device memory. In the sense, you could expose the entire device memory to the host system. So it need not be only a private memory. So given that kind of arrangement, so it defines two bias modes, right? One is called as a host bias and the device bias. So when the device memory is in the host bias, what happens is the CPU can actually access the device memory freely, right? Whereas if the device has to access its own memory, it has to go all the way to the CPU and request for request the CPU or the host agent to resolve the cache coherency, and then only the CXL device can access its own memory. So that's called the host bias. Whereas in the device bias, the device can freely access the device memory without, let's say, consulting the host, and the host will not be even aware that it is actually accessing the device memory. So these are the two bias mechanisms. So bias is defined at the page 4 kilobytes in CXL. Then there is a type 3 CXL device, which is just a memory expander. So it is, for example, it could be considered as just an extension of your host memory. So where read and write happen to this, CXL device. So it is just a memory expander. So these are the three different types of CXL devices that are discussed in the CXL specification. So what are the enhancements that have been done to CXL.io? So here on there will be a little bit of a detail, but let's still try to understand. So actually, because we are talking about a coherency domain in the context of CXL, it is important for the CXL device to know about the system level resets and the system state transition, power transitions happening, right? So at the transport level, so what happens is the CXL has defined some vendor defined messages which are type 0 messages, right, which go all the way to the endpoint to send the power management messages. So if you see, the host sends what is called as CXL power management vendor defined message. Let's say for the example of warm reset. So this message is sent to the CXL, and then in turn the CXL could do, for example, the flushing of its cache, and it could do other housekeeping operations inside, and then respond back with the CXL power management vendor defined message, and then the rest of the power down or the reset could proceed, right? So this is again enhanced in CXL. And some of the optional PCIe features which are required for CXL are data poisoning at the TX level, and address translation, and traffic classes. TC0 is mandatory, and so you could implement other traffic classes in order to get a better quality of service, and advanced error reporting is also to be implemented, right? And one more important feature that is defined in this CXL is what is called as deferrable memory write, right? So memory writes are posted, right? So which means the agent that wants to write just sends the write command, and it just forgets, right? So there is no completion or whatever that is returned back to the requester. So such a transaction is called as a posted transaction, and in PCIe the memory writes are posted. Okay, so why they are posted is because they aggregate multiple writes from various multiple write requests, and then they send it over the link in order to utilize the bandwidth properly. But here you have a feature called as deferrable write. In this case, the actually the upstream sends towards the downstream some non-posted memory writes, and the device could respond back saying whether the write completed or it has to be deferred. So this is a new feature that is added in CXL at the transactional level. Then CXL.Cache Protocol snapshot. So we have D2H and H2D. So device to host is called as D2H, and the host to device is called as H2D. So there are three channels defined, one for request, one for response, and another one for data. So you can flow either ways, from the device to host or from host to device. So if you see a device to host request, so they could be a read or a write towards a target memory, right? So if you remember, CXL.Cache is for those devices that cache the host addresses, right? So in this case, you assume this device wants to, let's say, cache certain memory locations which are there in the host, it could send a read, and it could also write to the target memory. So for example, there are certain transactions called as read current, read own, read share, dirty evict, memory write. So these are various requests that could go from the device to host. For example, read current, what it does is it is requesting the host agent or the host that the device is requesting to read the current data that is available for that particular address. And when the host responds, it will respond back saying, hey, here is this line, or here is the data that you requested, but then this data is in invalid state. That means the device cannot actually cache it. So basically, read current, what it means is it tells the host that, hey, I want to read this cache line, but I'm not going to cache it. Give me the latest copy of this data. So that's what read current is. Likewise, read shared, as we saw, means that the device wants to read the cache line and put it in the shared state. So that's what it means. Likewise, dirty evict is when the device wants to evict the modified cache lines, it would use dirty evict, and so on. Right. So there are various different opcodes and requests that are possible. I've just shown a couple of them here for example. So treating and understanding each of them will take a long time, right? And then you have H to D request, right? That is nothing but the request coming from the host towards the device. These are all snoop requests. As we saw earlier, these snoop requests basically change the state of the cache lines, right, inside the devices. So it could be a snoop data, or it could be a snoop invalidate, or it could be a snoop current. For example, a snoop invalidate from the host will actually invalidate that cache line inside the device, and the state of that cache line will be put as or marked as invalid. So basically, this is what happens, right? So when you get the snoop request. And then there is H to D responses. So they are nothing but some kind of signal towards the host, indicating about the transitioning of the state of these cache lines for the request that came from the host to device. And you could also have host to device response. So this host to device response are very important, because that's where what is called as a global observation, or a GO, right? It's called as global observation. So the host agent observes the write. It is a point where the writes to a particular cache line is observed at the system level, and then subsequently, you could go and invalidate if a write which is already cached in other caches. If a write happens to a cache line which is cached in the other caches. So that's called global observation. And then you have the H to D data and D to H data, which is nothing but the cache line itself, along with some information which helps in understanding that data. So this is what is the cache protocol. And then there is CXL.Mem. So as part of CXL.Mem, you have master and a subordinate topology there. So master is the CPU coherency engine, right? And the subordinate could be, let's say, CXL.Mem. So you have the M to S transactions, and then there are S to M transactions. So they are called as request without data. So it could be a read or invalidate that goes from invalidate is to invalidate. So all these things actually change the state of this cache line, right? So so it could be a request that goes from the master to say to read a data, and that will in fact will be responded with say a data, or there could be a response without data from the slave side or the subordinate side. So what we have to understand here is the CPU where the coherency engine or the home agent is present is going to behave like a master, and the CXL.Mem device will behave like a subordinate. There will be master to slave transactions and slave to master transactions happening between these two devices. So when a request is sent out from the master to the subordinate, so along with the opcode, the type of snoop that the master wants to perform is also sent. So this is what predominantly happens as part of the CXL.Mem protocol. So what we'll do is, like, we will try to put together all the things that we have seen so far in this one slide, and I think you will get most things clear, right, when we go through this. So far, as I told you, I've been focusing mainly on the transaction layer, right? So the link and again the ARM and rest of the layers, they are in detail in itself. So we'll not focus on that. So for next 5 to 10 minutes, let's focus on this particular slide. Okay? So here you have the home agent that is shown inside the host, and then there is a coherent bridge through which the coherent accesses go to the devices. So there are 3 types of devices shown. The first one is the type 2, which is an accelerator. It has to implement CXL.io, CXL.Mem, and CXL.Cache. And then there is a type 1 CXL device which caches the host data, and it has to implement CXL.io mandatorily and CXL.Cache as well. And then there is a type 3 device which is just a memory controller or memory expander, right? So CXL.io and CXL.Mem is implemented. So now let's say these bars that are shown is for the CXL. I want you to now focus on the figure towards your left hand side, CXL device, and then there is a peer cache. And so the peer cache is nothing but the CXL device of type 1, and then there is a home agent, which is the HA, and there is a memory controller. Right? The purple line shows the CXL.Cache D2H transactions, and the orange line shows CXL.Cache H to D transactions, and the green color shows the CXL.Mem. So the boxes I, E, S, and all those things, they show the cache line transitions or the cache line state changes. So initially, the CXL device requests for a particular cache line. So that cache line is in invalid state because the device still doesn't have it. So it is sending out a request to read that cache line in the shared state. So if you remember, shared state means that the data is available in all the caches, and the data is in sync with what is available in the cache and the main memory. So that is how this device wants to read that cache line. So it sends out the request to the home agent, and the home agent in turn, it sends what is called as snoop data as a H to D request to the peer cache, right? And that particular cache line is now actually with this peer cache in an exclusive state. That is what is shown as E. So in the meaning of exclusive state is this particular cache line is available only with this particular processor, and it is unmodified, which means it is in sync with the main memory. So so the home agent sends the snoop data on the H to D to this peer cache, and as a result, the peer cache puts that cache line in the shared state. It moves from exclusive state to shared state, and it sends the response back as response hit AC, which means this particular cache line got hit inside this peer cache, and also it transitioned from it has transitioned to the shared state. So that information is what you see here, right? As a purple line. And in the meantime, the home agent also puts up, because this is an unmodified data, it reads that data from the main memory and then gives the data to the CXL device. But before it gives the data, it gives what is called as GO-S. So GO, as I told you, is the global observation. So it is the point of coherency. So host agent now sends this GO-S H to D message to the CXL device, and as a result, the CXL device now moves to the shared state. It moves that particular cache line to the shared state from the invalid state, and the home agent also through the response sends the data that the CXL device requested. Right? I'll give it a couple of seconds so that it can sink in. Right? And then, let's say the CXL device now wants to have the exclusive ownership of that cache line. It puts out the read-own request, right, through the D2H to the home agent, and the home agent in turn sends the snoop invalidate. You know what? Because this is going to be owned by the CXL device, so this particular cache line has to be invalidated in the peer caches, and that's what happens, right? And the home agent sends the snoop invalidate to the peer cache, and then the peer cache now responds back with the respile hit SC message to the home agent. Now home agent now has observed this and then sends the global observation with E, which means now the CXL device can actually go to the exclusive state. And because there is the data that is already available, there is no data that is sent back to the CXL device. And now the CXL device can actually start silently writing or silently modifying this cache line how many ever time it wants, and then it starts putting this particular cache line from the exclusive state to the modified state and keeps writing as many times it wants. Once done, it has to now evict, and it's a dirty effect because it has been modified, so it sends the dirty evict information to the home agent. And again, the home agent in turn says go write pull, which means the home agent is now ready to receive this data that is going to be sent by the cache by the CXL device, because this data has to be now written back to the main memory as part of the eviction, right? So then it actually invalidates that particular cache line. The CXL device, after sending the data to the home agent, invalidates because this has been evicted and this cache line is no more valid, right? So it changes the state back to invalidate. And upon getting the data, the home agent sends the memory write request to the memory controller and writes the data into the memory and gets the completion in turn, right, from the memory controller. So this is what happens, right, when you put all these various CXL.Cache and CXL.Mem transactions together. Right? So as I told you, CXL.io pretty much comes into picture only for configuration discovery, so they don't take part in this active transfer of data, but you could still use that for say uncached data or some protected cache protected regions. If they are available, you could still go and use them for accessing the data. So this is how this protocol works at a high level. And some of the CXL use cases we have to talk about. So it can be used for volatile and non-volatile memory expansion. For example, you could have a CXL.Mem device and then have a DDR, a bunch of DDR connected to that Mem device, and it could act like a memory expander, right? An extension to the main memory. And you could also have the non-volatile memory or the NAND connected on this. And most of all, it serves as a low latency interface for the storage class memories, right? So storage class memories, I told you they exhibit low latency, and the existing PCIe bus is not very much suitable, and that's where people try to put it in the DDR slot. But again, the DDR slot is getting crowded, and so it is imperative to move these ACMs outside of the DDR. So again, CXL provides a nice interconnect to put this storage class memories there, and could have computational storage engine. So this is also possible where you have compute very closer to the storage or memory, right? You could offload some of the AI or ML operations, or it could be storage related functions like duplication and other functionalities offloaded to these storage engines, which very closely coupled to the storage and memory. And you could also have high performance accelerators, which I think is not a big no-brainer. I think we know that. Right? So CXL could be used for these kind of use cases. And so to conclude, my observation is that CXL is suitable for both compute, storage, and the networking world, right? So that requires low latency, high throughput, scalable, coherent interconnect. Each of, for example, you take storage and memory, so they need very low latency and high throughput bus, whereas networking needs networking needs very low latency, very high throughput bus. Whereas for let's say the new kind of accelerators that we are talking about, you will need memory semantics, right, which are also coherent in nature. So that is supported by CXL. So it kind of satisfies all the needs of both compute, storage, and networking. Right? That's how I see it. And so PCIe Gen 5 and Gen 6, now that we have PCIe Gen 5 already released and Gen 6 work is going on, so this will be accelerating the adoption of CXL. So in a way, we can say the search for an all-purpose, simple, cache-coherent off-chip interconnect ends here. Right? So we can say that. Of course, there are other buses like we saw CCIX, Gen Z, and OpenCAPI, but I think ultimately there is a whole lot of weight put behind this particular interconnect and the protocol. So that's what it is. That's what I wanted to discuss. Now I would probably open up for discussions.